Hello, everyone, and welcome to the Joy of Abstraction Book Club, Chapter 17. Thanks again to everyone at the Topos Institute for sorting this out and supporting us. And thank you to everyone who's following along and sending questions. I am definitely pushing the on-timeness making this video because I was at the Category Theory Conference last week and then I was traveling back to Chicago this week. I'm quite tired. So we'll see how this goes, but tomorrow my summer camp is starting, so I can't do it next week. And anyway, I'm really trying to keep on track with making each video before the next lot of questions comes in. So here we are. It's chapter 17, which is about duality. And so I think it's a really exciting chapter because it's quite short, but deep, really deep. And there are some great questions digging into some of the deeper meanings of it, rather than exactly necessarily the technicality. So let us just jump right in. The first question is, C and C-op feel like a one or two-dimensional thing. Is it possible to have three or more such categories whose arrows are turned around for each other, but not in some weird order them orthogonal way? And then this person says, which is quite sweet, I'm relying on your psychic powers for this one. I can't even articulate in words the question that I see in my head, which is kind of frustrating. So I'm wondering if you're thinking higher dimensionally, in fact, because a category has one dimension, it's got zero-dimensional objects, and it's got one-dimensional arrows. And these are the things that we can regard as being the opposite way around. But if we had another dimension, so I think you want an orthogonal dimension, then that direction could turn around independently of whether or not the one-dimensional one could turn around. And we will see this when we go into higher dimensions, because in two categories, there are morphisms between the morphisms, so there's a second dimension. And then you can take the dual with respect to the one-dimensional objects, and you can also take the dual with respect to the two-dimensional objects independently. And so then you can do one of them or the other of them, or both or neither. And that gets called op and co. So you have the possibility of the opposite, the op of a two category, the co, and also the co-op. And that will come back later on in the chapter on higher dimensions. So every time you get another dimension, you have a possibility of turning around those arrows independently of all the others. So if we had three-dimensional categories, you could turn around the one-dimensional arrows, the two-dimensional arrows, and the three-dimensional arrows independently of one another. So maybe that's what you're thinking of. Okay. Next question. Given the category and morphisms in that category, is there a general method for figuring out what the morphisms look like in the opposite category? For example, in the category set, there were several questions about this. Is there a precise method for determining what the morphisms are in the category set op? So I think I need to explain this opposite category a bit more, because I think there's a little bit of misunderstanding, because the opposite category really has the same arrows. And I think that I maybe misled you a little bit by starting with some examples saying things like, is the mother of, and then what can we say, or is parent of, and then what can we say in the opposite direction? We can say, is a child of. But we don't have to express that morphism differently. Okay, let me just get the whiteboard. So in set, a morphism from A to B is a function from A to B. In set op, a morphism A to B is a function B to A. That's it. So all we're doing is we're just regarding the morphism's source and target to be the other way around. So whenever you see any kind of arrow, and I think this is where I drew, perhaps this is where I drew the picture of a giant arrow. Let's see, did I draw a picture of a giant arrow? I did draw a picture of a giant arrow. So when we draw an arrow, this is how the whole thing started. The whole chapter started because I said, when we draw an arrow, the usual convention is that this is the back of the arrow and that's the front, and we follow the arrow in that direction. But you could just decide to call it the other way around. You could just decide that actually this end is going to be the front of the arrow and that end is the back of the arrow, and you could do it that way. You wouldn't have actually changed anything about the arrow, and you wouldn't have changed anything about the structure. So when we go into set op, we're not changing anything about functions, and the morphisms aren't any different. They're still functions. It's just that we're regarding the sort of back end to be the source of the function and the front end to be the target of the function. And so this is still just a function from B to A. We've just decided to regard A as the source and B as the target. So that's all that happens. And there are several questions about that. So perhaps I'll go on. So the next question says, the definition of an opposite category tells us that a morphism F from, so a morphism F in C from B to A is a morphism F in the opposite category in the HOMs from A to B. So this implies that F can have a source of B and a target, a source of B and a target of A in one category and the other way around in the opposite category. Does this mean that a single morphism can have two different sources and two different targets? So sort of yes, but I would say that that's not quite the right way of thinking about it, because each morphism has a source and target in any given category. So F regarded as a morphism of C can only have these source and target, B and A. F regarded as a morphism of C op can only have that source and target. So in any particular category, it can only have one source and target. But it can be all sorts of things in other categories, just like the fact that, for example, the numbers take on different properties in different environments, and in some place something could be indivisible in one place and divisible in another place depending on what we've got there. And so you can't really talk about a morphism without saying what category you're thinking of it in. But yes, things can take on very different properties in different categories. So another question: if F is a morphism with domain A and codomain B in a category of sets and functions, that's exactly this, then in the opposite category, F is a morphism with domain B and codomain A. Yes. So another way of putting it is, given a function from A to B in set, this is a morphism B to A in set op. But as I said in the book, I really prefer never to write down the morphisms the way around they are in the opposite category. The opposite category is a tool. We don't usually think of it in its own right. It's a tool that we use, and we usually keep the morphisms the way around that they are in the actual category C, and just think about things backwards, because this, as you can see, gets pretty confusing. So if I've got a function from A to B, I would prefer never to write it as B to A, or as I did in the book, put some kind of blob on it to show that this is not representing any kind of function from B to A now. It's just formally a morphism from B to A in set op, which I've sort of slightly gone out of order. So I'm going to make a note of the question I left out, because somebody else said, I've seen it said that opposite categories are just a formalism. What does that mean? What that means is that we haven't really done anything. We've just regarded something differently, and it turns out to be surprisingly powerful. So set op is not any different, is the same information as set. The category of sets and functions and the opposite category, it is exactly the same information. So we haven't really done anything. We've just decided to write things down differently. It's kind of like if we decided to write English from right to left instead, then it would just be a formal difference. We wouldn't have actually made a new language. If I just wrote the letters the other way around, if I wrote this way, then I wouldn't have made a new language. I'd just be doing something formally different. So I think that's what it means. And I do know that the dual category is quite confusing when you first see it, but it is remarkably powerful. And somebody else said, okay, I need to now mark down which questions I've done because I'm sort of going out of order. Somebody else said something about it, the remarkably powerful. Yes, someone said, could you expand more on how duality is a remarkably powerful concept? So the main reason why I think it's remarkably powerful is, well, there's two points to that, isn't there? Aren't there? There's first that it's powerful, and second that it's remarkable. So it's the remarkableness is that the opposite category really hasn't done anything. And so it's a kind of unreasonable amount of result that you get from not really having done anything. And so that's why it's remarkable, because really nothing is going on. I suspect that most of the questions are coming from overcomplicating the situation and trying to understand what the morphisms are in the opposite category. The morphisms in the opposite category are exactly the same. You don't have to think of them as new things. That's the point. They're exactly the same things. You don't have to try and understand what a function is if it's going backwards. It's still going the same way. We're just regarding it as going in the opposite direction. And this is powerful because of the Bogov principle, the kind of buy one, get one free. Every time you prove a theorem, you get the dual theorem for free, because if you prove that a theorem is true in any category, C, then in particular, it must also be true in the dual category, C op. And so you immediately get a dual version of the theorem for free. So just like everything we proved about monics is immediately true for epics, because epics are just monics in the opposite category. And when we do anything about limits, a limit in C, so we can do things like products. Products are a form of limit in C. If you take products in the opposite category, then you get, that's the concept of a co-product. And then whatever you've proved for products, you immediately get for co-products for free without having to do it, because it's just true in the opposite category. So for example, you get that products are unique up to canonical isomorphism, preserving something or other, and then you immediately get that co-products are also unique up to unique isomorphism because it's true in C op. So whenever you've proved something for all categories, then you immediately get it in the opposite category as well, and so you get all this stuff for free. Now typically you don't actually write down morphisms in the opposite category. So for example, when we look at products, we'll see that products are diagrams like this, satisfying some properties. Now, when we write them that the co-products, what we're going to do is we're going to turn every arrow around. So the co-product looks like this. But we don't actually draw it in the dual category. We still draw it in this category. But what we've done is we've taken this diagram as if it were in C op, which means that this arrow from the top to the left in C op is really an arrow from the left to the top in C. And so that's the thing we draw. And so what we really do, while abstractly we're thinking about this diagram in C op, in practice, what we do is we turn all the arrows around on the page. And it turns out to be remarkably powerful, kind of unreasonably powerful in a way. So that's what I would say about that. So now I've answered that question. So someone else has said, would you demonstrate what the dual of the category set is, please, where the morphisms are functions? So in the dual, this is another question of, I think I've answered it already. In the dual, the morphisms are still functions. So in the dual, the morphisms are still functions, and composition is still just composition of functions. It's just that we've regarded it the other way around. and I think I did this on page 229. So the warm-up exercise is a factor of and is a mother of. We're really just to get us warmed up about the idea of regarding arrows backwards. I realize now it may have led you astray into thinking that there's some way of thinking about functions backwards. There isn't really. So it just is that in set op, we regard the morphisms to be functions, but we consider the source and target to be the other way around. So in set op, I've already said this, so I'll say it again. A morphism B to A in set op is just a function from A to B. It's just a function from A to B. And then composition is just composition of functions. There really isn't anything different going on at all. So someone else says, when given a particular category, when, if ever, is it important to determine the meaning of the opposite category? And very rarely, there are some specific examples where the opposite turns out to have interesting meaning in its own right. For example, actually the category of finite sets, the opposite of the category of finite sets, turns out to have some interesting meaning because it turns out to be what you get. Let me see if I'm doing this correctly. I think if you generate products freely, so it turns out to be the free finite product category on a single object, and that's kind of interesting, and it's the opposite of the category of finite sets. But mostly we just use it as a tool and we don't really think about its meaning. Somebody else said, does transposition give an isomorphism between the category of matrices and the opposite of the category of matrices? So yes, the category of matrices, we'd better say, I mean, it usually has to have entries in a field, but let's just call them real matrices, has objects are natural numbers. Ooh, that's not very well written, is it? Natural numbers. And a morphism, n to m, is an n by m matrix. Now, it's true that arguably it maybe ought to be an m by n matrix for various reasons, but I personally can never remember what an n by m matrix is or an m by n matrix is either. And it doesn't make any difference because one of these situations is the opposite of the other. So supposing you took a morphism n to m to be an n by m matrix in mat, then in mat op, a morphism from n to m would be an m by n matrix. Good luck following the words of that. But the point is that there isn't any real difference between these, which is why I can't remember which one is which. It's rows and columns, but I have no idea which way around is which, and I have no recollection of when you're going from an n-dimensional vector space to an m-dimensional vector space, whether you're doing an n by m matrix or an m by n matrix. I think it's this way around because I know it's the wrong way around, and I've put in a little comment for the paperback version, whose corrections I'm doing at the moment. So the point is that this is a highly symmetric situation. You made an arbitrary choice about which way around you're going to consider this morphism to go. And whenever you make an arbitrary choice, the other one really ought to be to give you the same result. So this does give us, I suppose, an isomorphism between mat and mat op. And the question then says, what do isomorphisms between C and C op mean? So we will see that isomorphism is a slightly too strong concept for categories because we should really talk about equivalences of categories rather than isomorphisms. But the general idea here is that if a category is self-dual, then there's something quite special going on. So if it is possible to make an isomorphism between C and C op, then that means that each object gets paired with a partner object over here. So in mat, the natural numbers just went to the natural numbers. But in general, we would have to pair every object with some other object, which I'll call a dagger, in such a way that a dagger dagger is A. And that's already a sign that something slightly too strong is going on, because we've got an equality between objects. But then we would also need every morphism from A to B. Now, this is where it's a bit confusing whether we're writing arrows in C op or not. So it would need to go to a morphism in C op from A dagger to B dagger, i.e. actually a morphism going backwards in C. So this one is in C op. And then some conditions showing that this is functorial and that it's actually an isomorphism. And this is the reason I've written them as daggers, is because they're called dagger categories. Well, there are some more conditions. I think dagger categories are monoidal, but dagger categories are an example. And it's it's a situation of duality where every object in a category has a dual object in a category inside the category, together with every morphism having a dual morphism that turns us backwards. And it's quite interesting. So somebody else says, I've read that the quantifiers there exist and for all are dual to each other. However, when doing proofs, it's very important not to mix up there exists and for all. But in other examples, we seem to be able to mix something up with its dual because they're really the same on some level. I'm not sure about that. I don't think we're supposed to mix up something and its dual. I think we're supposed to use the dual to understand new things. And so there exists and for all a kind of dual to each other in logic, in the sense that they negate to each other. So there does not exist. So there exists X such that P of X is true, whoops, negates to, maybe I'll draw it underneath, negates to, for all X, P of X is not true. And that's kind of the sense in which they're dual to each other via negation. So yes, dual concepts are not the same, but they are, you take to get the dual concept, you take the concept in the opposite category, right? So you have, it's the process that I call making a souped up category. So you have a category C, and here you have a category, the opposite category is C op. So whatever structure you have here, you can look for the same structure over in C op, but then reinterpret it back in C, where it will become something different. So for example, it's like the products. If we take a diagram like this in C, you can go, oh, let's look at that diagram in C op. And it looks like that in C op. But when you reinterpret it back in C, it looks like this. And so this diagram is not the same as that one in C, it's the opposite, it's the same in the opposite category. So it's not actually the same, it's the dual. Okay, hope that made some kind of sense. Right. So now some more specific questions. Page 227 was the example of A as a parent of B. What if we say instead is a mother of? Then we would have no dual that preserves this information. So this is where I think maybe the warm-up examples led you in a slight wild goose chase situation, because A is a parent of B can be regarded as the other way around by saying B is a child of A. But we could also just say B is someone with parent A, which is a bit of a cop-out, but this is me trying to demonstrate that it really is just a formal situation. So if we started with A is a mother of B, we could just turn it around and say B is someone whose mother is A. Right, so the next question on page 228, someone says F and F op equal, isomorphic, or something else. But I don't actually see any F ops on this page. So the question is about F and F op. But I don't think I ever wrote F op. I wouldn't write F op because we don't actually take the opposite of morphisms. We take the opposite of the category, but the morphisms stay the same. So I would still call those F in the opposite category, and they're really the same morphisms. So now someone else says, do analogous pairs in C and C op exist in general? What are they? So usually when we're doing the opposite category formally, we don't try and interpret them, we just turn it around. And so F, it just becomes F in the opposite category. What we've regarded as the opposite way around are the source and target, but it's still just a morphism F, it's the same morphism. If I regard this pen from the opposite point of view, it's still the same pen. I haven't changed the pen. So somebody else, I think all the questions are basically on that topic. So someone says, it seems that the dual of a function is not uniquely specified. Remember, we don't take the dual of functions, we take the dual of a category, and we regard the functions the other way around. So this question says, for example, if there are two daughters with the same mother, then F could be a non-injective function is a daughter of. I think this is mixing up different metaphors. So in that case, if you're thinking about a function, the is a daughter of isn't a function, it's a relationship. What this person is saying is talking about a non-injective function is a daughter of. But if we're thinking of it as a function, then it's going to be a function. So maybe there are two people. So there's person A and there's person B, and person A is a daughter of C, and person B is also a daughter of C. Then in the opposite category, there would be two morphisms, one because A is the daughter of C and the other because B is a daughter of C. If you're doing functions, if we had a set containing A and B and a set containing C, and this is a function F going from this set to this set, in the opposite category, the function still goes from that set to that set. We're just regarding it in the opposite direction. So in the opposite category, in set op, in set op, this F is a morphism y to x, but it's still the same function. The function hasn't changed. So the important thing is to be able to regard it both ways around at the same time. So you can think of it as a function from x to y. So it is a function from x to y, but you can simultaneously think of it as a morphism from y to x. And so I think this is one of the reasons I often talk about pure mathematics as being a discipline for being able to think about different points of view at the same time. We can hold both of those points of view in our head at the same time. It is a function from x to y. we can think of it as a morphism from X to Y in set. We can also think of it as a morphism from Y to X in set op, but it's still the same function. It's just several different points of view on the same function. Okay, so someone else said a couple of questions regarding the alternative definition of categories. First of all, should we understand this definition as itself being a category in set with two objects? So the alternative definition of category starts with a set of morphisms and a set of objects and source and target maps, and then composition and identities. This diagram looks like it's a diagram that, like a category diagram, where this is an object, this is an object, and these are some morphisms. But that's not really quite the right way to think about it. What we're doing is we're drawing it categorically inside the category of sets. So this is now a diagram inside the category of sets defining a category. Now you could have a category with an object here, an object here, and a parallel pair of morphisms. It doesn't really, I don't think it really gets us anywhere to think of the definition of this as a category rather than thinking of it as the definition of a category. I know that didn't come out sounding entirely clear. So let me try again. I suppose there's a sense in which you can think of this as a little, so it's not really a category. So I'm getting a little tongue-tied because it is this is how you define internal categories inside other categories. And so once you have defined a category like this as this diagram with these morphisms in set, you can then just put that inside other categories V, and then you get the concept of an internal category inside V. But while you can make a category that looks like this, that's not quite the point of what we're doing there. So I think maybe, yes, you can think of it as a category with these sets and these functions as its morphisms, but I'm not sure it really gets us anywhere. Second question, is it true to say that C1 can be cardinally bigger than C0, but not the opposite? So that, I think, would be a yes, because C1 has to have at least an identity morphism for every object in C0. So C1 can't be smaller than C0, but it can be bigger than C0. And finally, do you ever find situations where there is a symmetry between C0 and C1? I'm going to say no, because of this condition where C1 has to contain an identity morphism for every object of C0. But C0 doesn't have to contain anything for every object of C1, for every element of C1 in quite the same way. So it has to things have to get mapped there, but really C0 is kind of contained inside C1 via the identities. So unless it were, right, and then there are really different structures. So the composition structure is on here, really not on C0. So unless C1 was the same as C0, I'm not sure that there would ever be really a symmetry situation exactly. Anyway, that was quite a lot of questions about the meaning of the dual category. I hope that that's a little bit clearer, and I hope that it will in particular get clearer when we move on to the next chapter, which I think is about products and co-products, because you get to see it at work. I definitely remember finding it really confusing at first, but once you see it at work, you see that you're not really working inside COP, you're using it as a tool. It's almost like a trampoline. You bounce off it and come back to where you are. And that is the principle of souping up a category, where you take a concept inside your category and then you think, okay, I can do this concept inside any souped up category based on C now, but I'm not going to stay there. I'm going to reinterpret it back in C, because that's where I'm really working. So finally, some praise. Thanks for your dedication. I loved this chapter, someone says. Oh, thanks. So did I. Thank you, Heartface. Still catching up. Thanks for this book club. These last 2 chapters were fantastic. Very good. Thank you for all the work you put in to continue the book club. Thank you. And thank you to everyone at the Topos Institute who is helping the support of this book club. I look forward to continuing with products and co-products. Things are getting really involved, and thanks for still being here. Bye.